So by using various tests, we have to verify whether it is convergence or not. So for what we have seen is geometric series we have seen. So first I want to verify. First let me look at the terms of the series n is running from 0 to infinity. So you have to attack the problem like this if it comes in exam. So from the beginning you have to verify all the tests which one will useful. Okay. So 1 upon 1 factorial, 1 upon 2 factorial, right? Plus 1 upon 3 factorial, plus 1 upon 4 factorial, plus up to so on. Okay. So now this is 1 plus 1 plus 1 upon 2 factorial, that means 2 only, plus 1 upon 3 factorial, which is 6. So let me write those things. So this will be, right, 1 upon 6. Next, plus 1 upon 24, 4 factorial means 24, plus up to so on, right. So now, is it geometric series? Verify. So a2 by a1 is 1, right? So a2 by a1 is not equals to a3 by a2. So a3 by a2 value how much? A3 is half. Half by 1 is half. So this value is half and this value is 1. Therefore it is not equal. Therefore it is not geometric series. It is not geometric series. Okay. So therefore geometric series test we cannot apply. So like this you keep on cancel out the existence tests. Right? So now geometric series test we cannot apply now. So next one, nth term divergence test. So now for that, what we have to do? Limit n tends to infinity. Limit n tends to infinity 1 upon n factorial. Right? What is this? It is 1 upon infinity factorial. That means 1 upon infinity is 0. So therefore, nth term divergence test we cannot apply. Nth term divergence test. Okay. Next, so this is also over. Divergence test we cannot apply. We cannot apply. So once it is also over. Next, so therefore first one is not working out, second one is also not working out, and third one what we have seen is next one, P series test can we apply? Look at this. So for P series I want the nth term of the series should be in this format, n power p, right, where n is running from 1 to infinity. It should be in this format, but it is not like that. It is n factorial, therefore I cannot apply P series test. Okay, so P series test cannot be applied because nth term of the series should be in that format only. There only we can apply. So P series test cannot be applied. So this one cannot be applied. Next one, fourth one, logarithmic P series test, right? Again, for logarithmic P series test, n is runs from 2 to infinity, 1 upon n into ln n raise p. Ln raise p. Again here, the nth term should be n into ln n whole power p, but it is n factorial. So again here we cannot apply logarithmic P series test. So continuation to that, and we have integral test, right? So integral test, for the integral test, 1 by n factorial, so clearly it is a continuous function, right? So integral test, for integral test, yeah. So 1 by n factorial is continuous and it is positive valued function, right? It is decreasing function, fine. So it is satisfying all the three conditions. Then we need to calculate what is the integral value. So integration f of x dx. So this value we need to compute, but here it is somewhat difficult to compute this integral. 1 by x factorial into dx. So this is very difficult to compute. Because 1 by x factorial means what? Integration 1 upon x factorial, x into x minus 1 into x minus 2 into, right? So up to so on into 1 last term into 1. So dx. So how to evaluate this? So this is somewhat difficult one. It is not so easy. Evaluation of this integral is not so easy. So that's why we are dropping this test. So if the integral evaluation is very simple, then I can proceed integral test. But here integral evaluation itself is become difficult. So that's why I'm stopping uh, this test, integral test. Okay. Then let's move on to the next available test, comparison test. Okay. So now by comparison test, what we have? So series n is running from where to where 0 to infinity 1 upon n factorial. So this will be 1 upon, so 1 plus 1 plus, directly I'm writing 1 upon 2 plus 1 upon 3 factorial, so 6 plus 1 upon 24, same what I have written there, up to so on. So this I am writing as, which is, so this one less than or equals to, look at the first term, 1 is less than or equal to 1 again, right? Second term is again 1, again 1 is less than or equal to 1 again, right? 1 plus 1. Third term 1 by 2 is less than or equal to 1 by 2 again, right? Look at the fourth term, 6 is always more than 4, so 1 over 6 is less than 1 over 4. So therefore this 1 by 6 less than or equals to 1 over 4. So therefore plus 1 over 4, 4 I can write 2 square. Indirectly I am generating geometric series right hand side. Look at next 24. 24 is more than 2 power 3, 8, right? So 1 upon 24 is always less than 1 upon 8, that means 2 power 3. So therefore 1 upon 24 is less than or equals to plus 1 upon 2 cube. So likewise I can write one next term is 1 upon 2 power 4 up to so on. So therefore indirectly this will be, so 1 plus series n is running from 0 to infinity, right? 1 upon 2, right? So if n is 0, 1 by 2 4 0 is 1, so first term is 1. So from here onwards I'm generating, from second term onwards this series will give the terms. If n is 1, 1 upon 2, n is 2, 1 upon 2 square and up to so on. So now clearly I can say that, so this is 0 to infinity 1 upon n factorial, and this is less than or equals to 1 plus series n is running from 0 to infinity 1 upon 2 raised n, 1 upon 2 raised n. So clearly it's like so an is 1 upon n factorial here, right? And next bn is, so cn, let's write cn according to theorem comparison test. Cn is 1 upon 2 power m, I'm taking except this first term. Okay, so therefore see why am I neglecting this one, because already have seen an is less than or equals to cn for all n more than some capital N, right? After certain stage it has to satisfy. Okay, see, for example, if we're having two sequences, first one is like 1 2 next 5 6 7 8 9 like this, okay, up to so on. So assume this is first sequence, second sequence minus 2 minus 5, next 9 10 11 12 and up to so on. So assume this is sequence an, and this is sequence an, and this one is sequence bn. Okay, now can I say that an is less than or equals to bn? I cannot say, because see 1 is not less than minus 2, right? See an first term is 1, here bn first term is minus 2, so 1 is not less than minus 2. Clearly 2 is not less than minus 5, but third term onwards 5 less than 9 correct, 6 less than 10 correct, 7 less than 11 correct, 8 less than 12 correct. So it is true for all n more than or equals to capital N is equal to 3 now. After certain stage this inequality is true. First few terms are not satisfying. First few terms means 1 and 2 here, and here minus 2 and minus 5. These terms are not satisfying here. 1 not less than minus 2 and 2 not less than minus 5. That's what, right? But here onwards, from 5 onwards, 5 less than 9 correct, 6 less than 10 correct, next 7 less than 11 correct, 8 less than 12, correct, like that. So this condition is satisfying from third term onwards, like that. So this is enough for me. So first few terms are not satisfying the condition, it is not required according to the theorem. Okay, but after certain terms, infinitely many terms need to be satisfied that condition. Here look at, from third term onwards, each and every term satisfy this condition. Therefore, I can apply this one, a n less than or equal to bn for these two sequences. Similarly here also, after certain stage only this inequality need to be satisfied, not required each and every term. If each and every term is satisfying, that is more than enough. Okay, but what is our goal? After certain stage, infinitely many terms need to be satisfied this condition. Then we can apply the comparison test. Hope you understood this. Okay, so a n less than or equal to cn, a n less than or equal to cn for all n more than or equals to capital N. So therefore, what is series cn according to comparison test? Series cn is equal to series. What is cn? Okay, let me write 1 plus. Okay, 1 plus, or simply write this one. Okay, it's not required. Okay, leave it. 1 upon 2 power n. 1 upon 2 power n, where n is running from 0 to infinity. N is running from 0 to infinity. So now, this series, is it converges? Yes, it is converges. To which number? Since it is geometric series, it is converges to a by 1 minus r. First term is, look at, so this is only, right? So this series only we are writing, right? So first term is 1. So a by 1 minus r. What is our geometric ratio? Half. So what is the answer now? It is 2. So therefore the sum is 2. So therefore, what I can say now here? So therefore, series Cn converges. Cn converges. So therefore, by comparison test, isn't it? By comparison test, we are having convergent upper bound, right? By comparison test, what we can write here? So this will be series n is running from 1 to 0 to infinity, 1 upon n factorial. This is less than or equals to, look at the series sum is 2 and in front first term is 1, so 2 plus 1 is 3. So overall LHS value is 3. Therefore this series is less than or equal to 3 and this series is having positive terms. Therefore this series sum is more than or equal to 0. So sum is more than or equal to 0 but less than or equal to 3. Therefore the sum is finite. So therefore the series 1 upon n factorial, n is running from 0 to infinity, converges. That's it. So this is the conclusion. What is the sum? We don't know. Sum I am not going to find by comparison test. Comparison test will gives you only status. Is the sum is finite or not? That's it. Convergence means sum is finite. Not convergence means what? Sum is not finite. That means sum is infinity, plus or minus infinity. But here it should be plus infinity. If you want exact sum, what will be the sum? You have to apply the general technique for this particular problem. Look at the particular sum of this series. See, what is e power x? You have seen already. E power x is x power 0 by 0 factorial plus x power 1 by 1 factorial. Okay, it is a Taylor series. You have seen in PUC this expansion. If not, just Google it. You will find this e power x expansion, 3 factorial plus up to so on. This is e power x expansion. Okay, now if you substitute x is 0 or x is 1, you substitute. So to get e power 1 is e only. X is 1. 1 power 1 is 1 and 0 factorial is 1. So first term is 1 plus x is 1. 1 power 1 is 1. 1 by 1 factorial. 1 by 1 factorial. And substitute x is 1 here. In both I am substituting x is 1. 1 square is 1 by 2 factorial. Next 1 by 3 factorial. Indirectly this series only given to us. Look at this only we need to complete it. What is the sum of this series? So now this sum is e indirectly. So what is e value? 2.73 approximately. The sum is approximately 2.73. Therefore, directly series n is running from 0 to infinity, 1 upon n factorial. So directly I can write this value is 2.73 or e, which is 2.73. Therefore, the sum is finite. Therefore, this is converges. So this is the general technique. You can find the sum. You cannot find sum of each and every series easily. Here, since you know this formula, then directly I can find the sum is e. So likewise. So, but by using comparison test, I can say only status converges. That means what, the sum is finite. But by using various techniques, you may find the sum. So it is also correct. Then sum is 2.73. So therefore, the series is converges. That's it. You can conclude like this also. It is also correct. So this is exact sum now. Hope you understood. So next continuation. Problem number 10. Find the convergence status of the series ln 1 upon n. Series runs from 2 to infinity. So for this problem, yeah, again you need to find the proper convergence upper bound or divergence lower bound. Okay. So series n is running from 2 to infinity, ln of 1 upon n. Or you can write this one, series n is running from 2 to infinity, ln 1 upon n means what? Ln n power minus 1, right? N power minus 1. Or you can write series n is running from 2 to infinity, minus ln n. You can write like this also. Okay. So therefore, what we can say, what is an now here? An is minus ln n, okay. Now let us find proper upper or lower bounds suitable. So now before that, you apply all test what we have seen. Geometric series, if it is not geometric series, then apply nth term divergence test. Look at nth term divergence test. What are you getting here? Nth term divergence test. Limit n tends to infinity minus ln infinity. So it is not equals to 0. Therefore directly by nth term test you can conclude. So by first method, so by nth term divergence test we can conclude. So limit n tends to infinity. Okay, an value. Now limit n tends to infinity, minus ln n. So which is minus infinity. So which is not equal to 0. Therefore by nth term divergence test, okay, by nth term divergence test, the series diverges. That's it. Over. So this is by first method. I can do it by second method also. Okay. Second method. Can I apply P series test? I cannot apply P series test because it is not 1 upon n power p. I can apply logarithmic P series test also, but because the nth term is not in that correct format, then it is not telescoping. Does telescoping series? Is it telescoping series? Check once. So ln1, so series ln upon 1 upon n, where n is running from where to where, 2 to infinity. Now you expand the terms. So this will be n is running from 2 to infinity, ln1 minus ln2, right? Ln n, sorry, ln n. Ln a by b, ln a minus ln b. So ln1 will be 0. So it is minus series n is running from 2 to infinity. So then what will get? Ln n only, ln n. Then expand the terms, what will get? So this will be minus of ln2 plus ln3, right? ln3 plus up to so on. So the sum ln2 plus ln3, so all these are positive terms, but we'll keep on adding, therefore this will be infinity. So overall it is minus infinity. So without any calculations, directly sum is minus infinity. Therefore the series is diverges. Therefore conclusion is, therefore the series diverges. That's it. This is second method. Can do like this also. Look at various methods you can apply. The series diverges. Okay. Problem number 11. Find the convergence status of this series. So first of all, what is the nth term we need to generate? So I can write this one as 5 plus 1 upon 3 plus 1 upon 2 plus root 1, right? Plus 1 upon 4 plus root 2, plus 1 upon 8 plus root 3. So look at first two terms are not in the fashion. So don't worry about those terms. So this I can write as 5 plus 1 by 3. I am writing as it is 5 plus 1 by 3. Don't worry about first two terms. But second term onward, the terms are in the passion. Look at 2 power 1, this is 2 square, this is 2 power 3, and root 1, root 2, root 3. So therefore, I can write this one as a series. N is running from 1 to infinity. Okay, 1 to infinity. 1 upon 2 power n first term. Okay, plus root n I am writing. Can I write? Check once. Now expand n is 1. N is 1, we will get 2 plus root 1. Look at 2 plus root 1, first term. Okay, first term is 2 plus root 1. Substitute n is 2, 2 power 2 plus root 2. Look at 2 power 2 plus root 2. Correct. N is 2 is over. Next n is 3, 2 power 3 plus root 3. Look at 2 power 3 plus root 3 plus up to so on. So therefore, from here onwards, from third term onwards, this can be written as like this, as a series. Okay. So now nth term we have, then go to the convergence status. So if you look at this, it is not a geometric series. Clearly 1 by 3 by 5 is not equal to 1 by 3 by 1 by 3. So 1 by 3 by 1 by 3 is 1. So it is not a geometric series. Likewise, each and everything you can verify. And by, look at, by using nth term divergence test. What about this series? Limit n tends to infinity, 1 by infinity becomes 0. Therefore, we cannot conclude. If it is not equal to 0, then only we can conclude by using nth term divergence test. Therefore, you cannot apply nth term divergence test. Therefore, and a p series test you cannot apply, and logarithmic p series test you cannot apply. So therefore, and one more what, telescoping series also we cannot apply, because terms you cannot write as something minus something kind of. Okay. So therefore, all these are we are dropping. Then we will move on to the next level, that is comparison test. So if I find suitable upper or lower bounds, then we can conclude. So what I am doing is, look at the series, this series. So look at 2 power n, the term I am taking 2 power n plus root n I am taking. Root n, 2 power n plus root n. So 2 power n plus root n is always more than or equals to 2 power n. Since n belongs to natural number set, right? N is a natural number. This number is always more than or equals to 2 power n. Look at 2 power n plus something we are adding here. But here only 2 power n. Therefore, this number is more. Then reciprocal this. So 1 upon 2 raised n plus root n. Plus root n. And this is less than or equals to 1 upon 2 power n. Look at, indirectly I am generating a convergence upper bound. Okay. So it's like, this is like an and is less than or equals to, it is like cn. Okay. Now what is series cn? Series cn is equals to series 1 upon 2 power n, where n is running from 1 to infinity, because here for this series n is running from 1 to infinity. So for this series n is running from 1 to infinity, therefore for this series also you take n is running from 1 to infinity. And now this is a geometric series which converges to a by 1 minus r, right? A by 1 minus r. Now what is a now? First term is 1 by 2. 1 minus, what is geometric ratio again? Half. So this will be 1. So therefore clearly what I can say, so therefore series cn, that is series 1 upon 2 power n, is converges. So you are having proper upper bound. Proper upper bound means what? Converges one, right? And this is converges. So therefore upper bound is converges. So therefore this lower bound is also converges by comparison test. So therefore by comparison test, by comparison test, what we can write? Series 1 upon 2 power n plus root n. N is running from 1 to infinity is converges. So this is converges, that means, so this thing is converges. So once it is converges means what? The sum is finite. Finite plus 5 plus 1 by 3 is also finite. So therefore overall, so therefore 5 plus 1 by 3 plus, so two terms we are adding, right? 1 by 2 power n plus root n is also converges. So this one is converges means what? So here this series is converges means the given series only, right? This series means it is given series only. Therefore the given series is converges. By which test? By comparison test we are concluding. Okay. Next. Continuation of problem number 12. solution. Test what we have seen. So it is not a geometric series. Series n is running from 2 to infinity. Ln n upon 2n cube minus 1. Can I apply nth term divergence test here? Look at once, nth term divergence test. Actually, you have to verify like this, and then you will get the idea. Nth term divergence test. It is not a geometric series, right? Then I am going to nth term divergence test. Can be applied or not for this? So limit n tends to infinity. Ln n divided by 2n cube minus 1. Then if you apply limit, what will you get? You will get infinity by infinity will get. Therefore, go to L'Hospital rule. So if you go to L'Hospital rule, what will you get? So numerator differentiation separately, so that is 1 upon n, and denominator differentiation separately, that is 6n square. And now apply limit n tends to infinity. Again, what will you get? This is 0 by infinity. 0 by infinity, large number. So we will get 0 only. So therefore, we cannot apply. If it is not equal to 0, then only we can conclude that is the series is diverges. But here exactly equal to 0 we are getting, therefore we cannot apply. And then we can move on to the next levels. So it is not P series, it is not logarithmic P series. Then go to the comparison test. So by using comparison, then you find the suitable upper or lower bounds, whatever. So n, since ln is there, so I am starting with n. So n is more than ln n. This is true. From where? From n is more than or equals to 2. Cricket series is running from 2. Substitute 2. So 2 is more than ln 2. That is true. And 3 is more than ln 3. 4 is more than ln 4. 5 is more than ln 4. That is always true. Right? Over. Assume this is inequality number 1. Because there are two numbers. One is ln n and the second one is 2n cube minus 1. So I want to generate that also, 2n cube minus 1. So next I am writing the inequality upper or lower bounds for 2n cube minus 1. So 2n cube minus 1 is always more than n cube. Can I write? Because here 2n cube means what? Actually n cube plus n cube, right? So n cube plus n cube minus 1 is always more than n cube only. Because why? Here 2 times n cubes are there, here only 1 time n cube is there. Understood? So therefore 2n cube minus 1 is more than n cube. So therefore 1 upon 2n cube minus 1, 2n cube minus 1 is less than 1 upon n cube. 1 upon n cube. And assume this is number 2. Right. So from 1 and 2, from 1 and 2, what we can say? So n is more than ln n. So first let me write the term ln n upon. So this is a given term. Look at the problem. Ln n by 2n cube minus 1. 2n cube minus 1. This is a given problem. And this one is less than. Ln n is always less than n. So ln n less than n. Numerator is over. Next denominator 1 by 2n cube minus 1. 1 by 2n cube minus 1 is less than 1 by n cube. So n cube. Okay. So therefore this is togetherly 1 upon n square. So now it is like an is less than cn kind of. An is less than cn. So therefore series cn is what? Series 1 upon n square. And this is converges by P series test. Is converges by P series test. P series test, because P is equal to 2 you are having, this is more than 1. So therefore by P series test it is converges. Therefore you are having convergence upper bound. Therefore lower bound also converges by what? Comparison test. Therefore by comparison test, the given series converges. The given series ln n upon 2n cube minus 1 converges. That's it. So this is by what? Comparison test. That's it. Okay. Next one. Yeah. Find the convergence status of this series. So again same story. So let us write. So an is directly I'm writing. So n cube upon n power 5 plus 5 times n power 4 plus 7. You verify all the test. If any you can attack this problem by any of the test, you can apply, no problem. Now directly I am doing this one by comparison test. So this one less than or equals to n cube. So n cube always less than or equal to n cube is okay, but denominator is n power 5 I am writing. Why? Because look at here, n power 5 plus 5 times n power 4 plus 7. This one is always more than or equals to n power 5 again, right? Since n is natural number, it is true. So 1 upon reciprocal is n upon n power 5 plus 5 n to the power of 4 plus 7. This is always less than or equal to 1 upon n power 5. That's what we did. So therefore 1 upon this one is less than or equal to 1 upon n power 5. So this will be 1 upon n square. Again, upper bound is series n square is converges, therefore lower bound is converges by what? Comparison test. Therefore, so it's like an is less than or equal to cn kind of. Therefore, what is cn? Series cn. Therefore, series cn is which is series 1 upon n square. 1 upon n square is converges by p series test. Okay, p series test by p series test. So therefore series cn is equals to series an, sorry. Now series an is series n cube by the given series n power 5 plus 5 n to the power of 4 plus 7 is converges by comparison test. That's it. Okay, next one more theorem number 8, limit comparison test. It's easy one. So before that, the requirements are first two series you have taken and the terms should be more than 0. Previous one for comparison test more than or equal to 0. Now it is limit comparison test. Comparison test and limit comparison test, both are different, and it's true for all n more than or equal to some capital N for some natural number n. Then the first statement is, if limit n tends to infinity, an by bn is L, where L is finite. Okay, here L is finite number which is more than 0. So positive finite number indirectly. Okay, if the limit is positive finite number, then both the series converge or diverge together. Okay, next one, if the ratio, limit of the ratio is 0, exactly equal to 0, then and bn converges. So if these two happen simultaneously, first one is what? Limit should be 0 and bn should converges. Then the conclusion is series an is converges. Okay, next one, limit value is infinity, ratio of the limit value is infinity, and bn diverges, series bn diverges. Then conclusion is series an diverges. Okay, first one is the limit value should be finite positive number. Okay, that means more than 0, finite positive number. Then both converge or diverge together, series an and series bn. Next, if the limit value is 0 and bn converges, then the conclusion is series an converges. So this is the conclusion, series an converges. Next, third statement, limit value is infinity, and see, it cannot be minus infinity. Why? Because look at an is more than 0, bn is more than 0, therefore the ratio also more than 0 only. Understood? More than or equal to 0, the ratio. So that's why it is positive only, infinity. If the ratio value is infinity, limit of the ratio value is infinity, and bn diverges, then conclusion is series an diverges. So roughly I will give the proof for this. You complete the remaining proof. So here, yeah, look at just one definition. So for example, sequence an is given to us. The sequence n is converges to L. So by definition, what I can say, for all epsilon greater than 0, right, there exists a natural number, n belongs to natural number set, such that what we can write, modulus of an minus L is less than epsilon for all n more than or equals to capital N. So this is by limit definition, right? So this is a limit definition. So by using limit definition, I want to attack this theorem. So same like this. So here an by bn is there. So what I can say, for all epsilon greater than 0, for all epsilon greater than 0. So first one I am doing, first one, for all epsilon greater than 0, there exists a natural number set n. Natural number n belongs to natural number set, okay, such that modulus of an by bn. Now, so instead of the sequence what you are having, an by bn is a sequence. Now here I can take, instead of an, I can take, this is my sequence. So this is my sequence. Okay. Now what is nth term? Nth term is an by bn. And if this one is converges to some L, then according to this I am writing the definition. So modulus of an by bn minus L, because look at the limit value is L right here. Look at the first statement. Limit value is L, it is already given. Then what is conclusion? Both an and bn converge or diverge together. That I need to prove. So modulus of an minus bn minus L for all n more than or equals to capital N. Okay. So this is by definition. Okay. So now the statement is true for all epsilon greater than 0. Then for simplicity what I am doing is, so let epsilon is equal to some 1 you take or 0 you take, your wish, whatever. Okay. Because it is true for all epsilon greater than 0, right? So for simplicity let epsilon is 1. Then what is the statement? Modulus of an by bn minus L is less than 1. Then minus 1 less than an by bn, okay, minus L less than 1. Then simplify. So add both sides L. So L minus 1 less than an by bn, an by bn less than L plus 1. Okay. So it is L minus 1. So what do you have now? L minus 1, L minus 1 less than an by bn less than L plus 1. Listen carefully. It's a very simple one only, not much difficult one. See, instead of epsilon is 1, you can take epsilon 2, your wish, whatever, because it is true for all epsilon, right? Epsilon is a number, real number. You can take any number, your wish. Now, so assume L minus 1 is some alpha, right? Less than an by bn. Alpha is a number, L minus 1 is a number, so alpha is a number. So L minus 1 is nothing but alpha. L plus 1 is nothing but some beta you take. Okay. So now clearly, let's multiply both sides with bn. So alpha into bn less than an less than beta into bn. Okay. So if you want, you can write since where alpha is equal to, I am taking L minus 1 and beta is equal to, I am taking L plus 1. Or you can take directly, no problem. You keep this one as it is, no problem. Just for simplicity I am writing alpha and beta, or you can keep L minus 1 as it is, no problem. So if you keep L minus 1 as it is, you get L minus 1 into bn, and here L plus 1 into bn, nothing else. Okay. This inequality, rightmost inequality. So case 1, an is less than some constant into bn. Okay. So look at by comparison test. This is limit comparison test, but I am using comparison test. Okay. So by comparison test, if series bn converges, or you can write beta also, no problem. You can write beta, no problem. Series beta into bn converges. If upper bound is converges, then series an converges. An also converges. Okay. So that is both are converges indirectly. Both series an and series bn converges. Okay. Next, case 2, diverges case, right? Both are diverging, I need to prove. So case 2, you look at the leftmost inequality, that means this one, alpha into bn. Okay. So alpha into bn, alpha into bn is less than an. Okay, again same story. By comparison test, series alpha into bn diverges, then series an diverges. Look at, again both are diverges, right? That is, both are diverges. Series an and series bn both are diverges. Then it's proved. That's it. We proved that both are converging or both are diverging togetherly. So that means that is by using comparison test only. By comparison test, if series bn is diverges, that means the sum is infinity. So series an is more than that infinity. That means what, series an also infinity. Therefore series an is diverges. So similarly, you try for second statement. If limit value is 0 and bn converges, you take. So bn converges you have to take, and this limit value is 0 you have to take. Then you have to prove that series an converges. And here what you have to take, only limit intensity an by bn is equal to L. This only you have to take. Then we have to prove both are converge or both are diverge togetherly. That already I proved. Similarly, third statement, you take this is infinity and bn diverges you take. Then you prove that an diverges. It's simple one, you try once. If not, I will explain next class. Try once. Okay. So this is about limit comparison test. Then attack some problems by using limit comparison test. Solution. Look at the same problem I did already, that is problem number 13 only, but I did by comparison test. The same problem I can do by limit comparison test also. So in this, I need to find a ratio, right? So here clearly an is, nth term is n cube upon n to the power of 5 plus 5 n to the power of 4 plus 7. So this is an. Now series an is with me. Now I need to choose bn in this. Listen carefully. For applying limit comparison test, I need to choose bn properly. But how to choose bn is matter, because you look at the theorem statement. Every time we need to compute what is limit n tends to infinity an by bn only, right? Limit n tends to infinity an by bn value I need to compute in all three statements. For that I require what is bn, right? But how to choose bn? Proper bn only you have to choose here. Okay. So then what we have to do is, our main goal is what is bn. So how to choose bn here? So bn you have to choose like this. You have to choose. This is a procedure actually. Bn we have to choose cleverly such that an by bn is equal to some l, which is l more than 0 finite and 0 or infinity, and then accordingly we can conclude. But here there is a technique for choosing bn. The technique is, look at numerator. Okay, as n becomes large and large, what is the numerator value? That means n is 1 crore, 10 crore or 1000 crores, 2000 crores or 1 lakh crores, then n cube is similar to what? So this is similar to, I am writing here itself, numerator is approximately n cube only, but denominator is approximately what? N power 5 plus 5 n to the power 4 plus 7. This is approximately equal to n to the power of 5. As n becomes large, as n becomes very large, denominator is approximately equals to n to the power of 5. For example, look at 1 crore plus 1 I am doing. For example, 1 lakh crore, 1 lakh crores plus 1. This is approximately equals to how much? 1 lakh crore only, right? That's what I'm doing actually, 1 lakh crore. So here 1 doesn't matter. So 1 lakh crores plus 1 is 1 lakh crore only. Same like that I'm doing. So the denominator n power 5 plus 5 into power 4 plus 7, as n becomes very large, this is approximately equal to n to power 5. So overall this is 1 by n square. So now this is our bn now. So this is our bn. So like this we have to choose bn, then only this theorem can work out. So this is a technique how to choose bn in this limit comparison test. Then everything goes smoothly. Then you find what is limit of the ratio. Limit n tends to an by bn value I want. An by bn. So this is limit n becomes large. What is an now? So which is n cube upon n raised 5 plus 5 times n raised 4 plus 7 into bn. so n square by 1. Okay, and this will be, so limit n becomes large, n to the power of 5 divided by n to the power of 5 is common, 1 plus, what will get, 5 by n you will get, isn't it, 5 by n plus 7 by n to the power of 5. Okay, so therefore this n power 5 cancel out. Okay, and then so therefore limit n tends to infinity, you apply the limit 1 by 1 plus 0 plus 0. So what will you get, 1. So 1 is more than 0, which is finite. So first conclusion, first condition. So therefore, what I need to write, by limit comparison test, by limit comparison test, by limit comparison test, both series an and series bn converges or diverges together. So here everything is depending on series bn. Now what is series bn? So therefore now conclusion is, so therefore series bn, which is nothing but series 1 upon n square, is converges by p series test. Which is series n cube upon n to the power of 5 plus 5 n to the power of 4 plus 7 also converges. That's it, over. Look at, by comparison test also I proved it is converges. Okay, so by limit comparison test also I proved it is converges. The status is remains same, the technique is different. Okay, and here one thing I want to remind you, look at the series bn. Series bn is 1 upon n square, which is converges by p series test. Such kind of bn only you have to choose. If you choose the tricky one like 1 upon n square into ln into sin n into tan n, if you are choosing like that bn, then the convergence status of that particular series is become difficult. So you need to easily prove that the convergence status of this series. So here clearly I can prove easily the convergence status of this one. So the convergence status of this series is converges by p series test. Look at how easily I am proving that it is converges. So that is the matter. So such kind of the series bn you have to choose. Understood? You should not choose the difficult bn here. Why? Because if you are choosing difficult bn here, what you have to do at the end, you have to find the convergence status of this series. There you will be stuck. So that's why choose the simple terms which are suitable. That's why you have to choose like this. Okay, similar problem, problem number 15, again same story. So directly I want to attack this. So what is an now? An is 2n minus 1 divided by n into n plus 1 into n plus 2. So it is cubic polynomial, right? Denominator is cubic polynomial. So this is approximately equals to, as n becomes very large and large, 2n minus 1 becomes 2n only. It doesn't matter, minus 1. Like 1 lakh crore minus 1 rupee. What do we get? Approximately 1 lakh crore only, right? That's what 2n minus 1 is, approximately equals to 2n. And denominator n cube, cubic polynomial. Therefore, n cube I am writing. Okay. So this will be 2 by n square. 2 by n square. So therefore, let bn is, I am choosing bn is 2 by n square. This is my bn. Okay. Then you proceed the ratio of the limit an by bn. Okay. So this is, so limit n tends to infinity. What is an now here? 2n minus 1 upon n into n plus 1 into n plus 2. Okay, into 2 by n square, so n square by 2. Okay, so now simplify this. So limit n becomes large. Okay, so numerator n cube I am writing out completely. So inside 2 minus 1 by n. So here one n I am taking out, already n square is out. So total n cube divided by denominator n cube. So each and every bracket I am taking one n common. From the first bracket one n common, second bracket one n common, overall n cube. So inside what you will get 1 plus 1 by n, right? 1 plus 1 by n. And the second one 1 plus 2 by n. 1 plus 2 by n. Now if you apply the limit value, what will you get? So n cube and n cube is cancelled out. N cube and n cube is cancelled out. So what will you get now? This will be 2 minus 0, right? 2 minus 0 divided by 1 plus 0 into 1 plus 0. 1 plus 0. So overall, what will you get? It will be 2 only. 2 is more than 0, finite number. Again by limit comparison test. So therefore by limit comparison test, what is series Bn? What is series Bn? Series 2 by n square. Can I apply P series test? Yes, you can apply. You take 2 outside, 1 by n power 2, that's it. So look at only this series is converges by P series test. Is converges by P series test. P series test. So therefore final conclusion is, so therefore what we can say? So therefore series AN, which is series 2n minus 1 by n into n plus 1 into n plus 2 is also converges. That's it. Okay. Next one. This one. Yes, look at this. I will give a hint. You try once for this. So take an is 1 upon 2 power n plus 3 power n. Then how to choose bn? I can write 1 upon take 3 power n is common. Then it will be 1 plus 2 by 3 whole to the power of n. If you take 3 by n is 3 power n is common. Okay. So therefore, as n becomes large, this is numerator approximately equals to 1 and denominator approximately equals to 3 power n. Why I have taken only 3 power n? Why not I have taken 2 power n is common? If I take 2 power n is common, what will get? 1 by 2 power n. Here inside 1 plus 3 by 2 whole power n. 3 by 2 whole power n. If I apply limit n tends to infinity, 3 by 2 power n, 3 by 2 power n, limit n tends to infinity, this will be infinity. This will be infinity, right? So that's why I am taking 2 by 3. So look at the geometric series. If modulus of r is less than 1, then limit n tends to infinity, r to the power of n value. What I proved? Check once. I proved 0, right? Look at the proof of geometric series theorem. So if r is more than 1, if modulus of r is more than or equals to 1, then limit n tends to infinity, r power n is infinity. I proved there. Check once. So therefore limit value is infinity if r is more than or equals to 1. So here what is r here? 3 by 2, 1.5 is more than or equals to 1, therefore limit value becomes infinity. That's what I am taking 3 power n is common. So therefore let bn is 1 upon 3 power n. Okay. So if you find the limit value, that's what you will get. Limit n tends to an by bn is supposed to compute, right? So here you will get into stuck if you are taking 2 power n is common. So what is an? 1 by 3 power n into 1 plus 2 by 3 whole to the power of n. Okay. Into bn. What is bn? 3 power n by 1. So therefore here 3 power n and 3 power n cancel out. Okay. What is remains now? So limit n tends to infinity, right? Limit n tends to infinity. Okay. So therefore, limit n tends to infinity. Now we are getting 1 upon 1 plus 2 by 3 whole to the power of n. Okay. Now this will be 1 by 1 plus 0 because it is 2 by 3. Since you write, since 2 by 3 is lies in the interval minus 1 to plus 1, minus 1 to plus 1. So therefore, limit n tends to infinity, 2 by 3 power n is 0 directly. Or you can write the standard formula, or you can write this one also. Or if minus 1 less than or less than 1, then limit n tends to infinity, r to the power of n value is 0. R to the power of n value is 0. So by using this, it will be 0. So therefore, this answer is 1. We are getting 1. So which is more than 0. So therefore, by limit comparison test, both converge or diverge together, right? So therefore, series Bn is what? It is a geometric series. It is converges. Converges to a by 1 minus r. What is a now? Series n is running from 1. So a is 1 by 3. 1 by 3 by 1 minus 1 by 3. So 2 by 3. So 2 by 3, 3 by 2. Right? 3 cancel 1 by 2. So sum is 1 by 2. Therefore, this series is converges. Bn is converges. Therefore, corresponding series an also converges. Okay, try once, complete this problem, and with this I will stop. I will do more problems by limit comparison test. With this I will stop.